Chang Na from Ohio Supercomputer Center. If some of you have attended the MOG, Ohio Supercomputer Center, typically we have the in-person meeting there. They are typically our hosts, have been for the last 7 years. Unfortunately, this year we have to go to this virtual. Um, Dr. Karen Tomko is the Director of Research Software Application and serves as the manager of the scientific application groups at the OSU, where she oversees deployment of software for data analytics, modeling, and simulation. Research interests are in the field of parallelization and performance improvement for HPC applications. She has been with OSC since 2007 and has been collaborating with me and my group for last 10 years. We have a lot of joint proposals, joint grants, a lot of MAPIC enhancements, and all also Karen and others have contributed. And Hee Chang Na is a senior scientific applications engineer at the Ohio Supercomputer Center. He is interested in performance analysis, system monitoring, and research environment development. He received his PhD in computational high energy physics from Indiana University, Bloomington. Before joining OSC, he worked with Milk and FPQCD collaborations in the Lattice QCD project. So today they will be talking about OSU INAM at the Ohio Supercomputer Center. Monday, if you remember, like Hari gave a high-level presentation of the INAM and its features. So Karen and Hee Chang will take it to the next level. In fact, we are working collaboratively in this project, and they have actually the deployment is one of the largest deployments where INAM is running in a production manner. So let me ask Karen and Hee Chang to share the slides, and let's welcome them for the talk.
Thank you, DK. Let's see. Just pulling up the slides now.
Sure.
Okay, so hopefully you're seeing the slides okay?
Go to the presentation mode if you can. The outline slides are showing on the left.
There you go.
Yes. Now the next slide is also showing.
Oh, I switched monitors. Let me share again and see if I can get it to share the right. There we go. How's that?
Yes, this looks good.
Okay.
We are on the second slide.
Okay, that's good enough. It is our outline. Actually, if I could go back, I wanted to introduce. So the INAM deployment at Ohio Supercomputer Center is a team effort, and I'm going to give an overview. Hee Chang Na is going to give a demo of using INAM at OSC, and then Trey Dockendorf does the deployment of INAM. He's in our sys group, and he's on the Slack channel. So if you have questions that are deployment and configuration specific, he's available there. So quick overview of OSC systems and our fabric, and then we'll talk about INAM at OSC. I'm gonna try to keep all this overview stuff to about 10 minutes, so there's lots of time for the demo. Right now, we have 4 systems on the floor. Actually, 3 systems, but 2 generations in our largest system, our newest system, Pitzer. And then our oldest system, Ruby, is still operational, but it will be it'll be turned off as soon as the Pitzer expansion nodes are made generally available to our community. But that means right now we have sort of the biggest fabric we've ever had. So we have here 4 generations of cluster hardware that we've purchased. We have 2 generations of GPFS parallel file systems, all on the InfiniBand. Our nodes, all of these systems have multiple types of nodes. They have kind of standard compute nodes, which are dual socket and different Intel variants. And then we have large memory nodes on all systems, and we have GPU nodes on all systems. Oops. Sorry about that. The fabric itself, we have one fabric, and that's because our file systems, our parallel file systems, are available on all of our clusters, so they're shared, and so they're all connected to one fabric. That complicates things, the biggest complication being multiple generations of fabric, and sort of, you know, each cluster has a topology when it's deployed, and then these all get integrated and connected to a single fabric. Right now, that's 139 IB switches in the fabric, over 1,700 compute nodes, 2 different GPFS clusters by different vendors. Our oldest cluster, Ruby, is FDR InfiniBand, and we have 2 generations of EDR, ConnectX-4 and ConnectX-5, different switch sizes and topologies in the clusters. And then routing, we use Mellanox's UFM for fabric management and routing. This, here's a diagram of the fabric from INAM. This diagram is produced from INAM. And you see, we have a level 3 fabric with 12 spine switches. Those are roughly over here in the middle. We have Owen's cluster has actually 2 islands with over 800 nodes. And then this is the Pitzer cluster with the expansion nodes. They're available to our staff right now. We don't yet have users on some of these. And then Ruby, the FDR cluster. And these are some of these in the middle here are storage, access to the storage systems. And then we have a few other servers and things for that are connected to the InfiniBand for infrastructure. We started working with OSU on this project. We tested an early version of INAM at OSC and started to run into some things different than they had seen in the lab. Right, their lab system was smaller and deployed differently. So when we put it on our system and we had multiple clusters and we had a different batch scheduler, a variety of things, they invited us to work with them on the FAMI project, which has been funded by NSF. About 3 years ago, it just wrapped up this summer. And so you can see the team there, the OSU group, and then Trey He-Cheng and myself at OSC. As part of this project, we've been running INAM continuously on our clusters for over a year now. Spring of 2019, we really started running it regularly, but it's iterative. So OSU develops a new version, we deploy it, we test it, and so we're pretty much still in a pretty active development, deploy, test mode. You can learn more about it if you weren't able to catch the tutorial on Monday. Learn more at the INAM website. Main features is that we can monitor the IB on our clusters in real time. We can profile node, get node profile data, IB switch counters, and correlate that with jobs. So that is really helpful for us to look at whether if we're seeing something unusual on the network or something unusual with some jobs, we can correlate those. And we have history, so a user could conceivably, right now it's only accessible to staff, but can look back at their job and see what happened with respect to what were the performance counters. And there's lots of searching and filtering. I think Hee-Chang will show you a lot of that. Our deployment, we have INAM deployed on one of our infrastructure servers. So it's not on a login node or anything. It's on one of our staff-only servers. It connects to our batch servers, and it connects to the clusters to read the counters, switch counters. It has 3 components: the web server, which is the user interface, the database, and we'll talk a little bit more about that, and then the daemon that collects the statistics. In configuring for OSC, first challenge was we were the first Torque Moab scheduled environment they worked with, so we had to make that work. We're actually now running 2 resource managers because we're migrating to Slurm. Our expansion to the Pitzer cluster is running Slurm right now. We don't yet have those job information for Slurm configured yet. That's a new project. As we migrate, we'll have the 2 resource managers available. We'll migrate 1 cluster at a time. So so right now we just have Torque Moab job data. Data collection, these are tunable parameters. We're doing collection at 30-second intervals for the fabric counters and 30-second intervals for polling the batch servers. And right now we're retaining job history for about a week. And with that, our database is about 56 gigabytes. And then we replicate the configuration file on the compute node so that for the Embed 2 integration. One of the things that we learned when we moved to OSC was that with the bigger fabric, some of the processes in INAM needed to be were slower with the bigger fabric than they had tested in the lab. So the team at OSU developed a multi-threaded fabric discovery and cached the diagram of the fabric, and so it's only updated periodically for changes in the fabric because they don't happen that often. And they're also with Trey providing some suggestions. They did some database optimizations so that we could purge the database without delaying insertions into the database. And also, Trey did a lot of work with the team on deployment and configuration, small things that could make it a lot easier to deploy in a production environment, at least for our production environment. And then Hee-Chang did a lot of the testing of the user interface and the user's perspective, and both made suggestions for things like searching by lid that would make it more convenient, and then I identified bugs as we encountered them. So we actually think it's been a great collaboration. Puya wrote it up for Perk, so you can read more about some of the details of these things, particularly the performance tuning work is described in there, and more about the tool's features on the INAM page. And with that, I'm gonna turn it over to Hee-Chang for the demo. While he's getting the demo set up, I can take some questions if there are any.
Questions?
Karen, can you stop? Okay, can you share the screen now?
Yes, you can proceed, Ichan.
Okay. Can you see the screen?
Yes, yes.
Fine? Okay,
Uh-huh.
thank you. Yeah, so then let me start. So I'm going to show a demo for OSU INAM on our 3 clusters. So this is the main page of INAM. And on the top panel, we have major features available on here, and hopefully I can go over each of them there. So let's go to the network view first. So this will draw the entire cluster with the InfiniBand network in a diagram that Karen showed a minute ago. So it's rendering. Hopefully it's showing up soon. Yeah, here we go. So this is a cluster view, and so each dot representing each node, and then the line representing the links between the node and switches, so that the red dots are the yes. So okay, and then when you hover over each element, and then it pops up the information, so that the name of this node is 00571, which which is referring to a OS node. And in this node, there is a job. It's currently running, and the job ID is 11049.176. So I identified that this cluster is OS. And you like to confirm. So it's just starting with O, so that it's OS. And then if I look over this, and then the node name is starting with R, so that it's Ruby. And this cluster starting with P, so that it's a picture. So we added like a 400 picture, new picture expansion node, so that more than 300 is actually for the picture expansion node, and it all appears on here. Because they are sharing the same InfiniBand networks. So let's see, find something more interesting. So I can actually look over one of node from here. If I select name and put the node name here, and then it allow me to finding out where this node is. Okay. So you see here has little brighter dot, and that's the node 00320. And I submitted and then currently I ran a job on this node. Then right click, open node info, and then I can dig into more detailed information of the node. So it's rendering the thing. So still running on. Yep. So it shows the CPU usage. This should be go up. So this is a real-time information. So it will refresh every 30 seconds. Yeah. And then I'm going to show more detail about this global MPI inter and intra-node data exchanges later, because if I click it, it will take a little time to show up. And on the real time, the information is not very interesting. So I'm going to skip that part. I just like to show that I can monitoring the real-time job information from the network view diagram. Okay, then other thing that we can do with network view is that I can look for historical view and change it to the job ID. And I ran a test job some time ago, and then I can put here the job ID number. Okay, let's move the cursor to the front. Okay. Yeah. So this job was a 16 node job, and it shows the diagram of the network for the particular job. So there is a 16 node around, and then I can identify which switches that involved with and which links that was used, and so on and so forth. And the more interestingly, I can play the previous job on here. So if I click play, and then it updates the the network status in the historical view. So there is a little playable bar here, so that it's representing time. It. And then let's go to look at the live jobs. So in this live jobs tab, it's showing all the running jobs in our clusters. It's not just a single, from a single cluster, it's from all 3 clusters. So currently, we have 1,420 jobs running, and all jobs appears here. And many jobs has no data from MPI process for this job because it doesn't use MVG2X. So I launched 3 jobs with MVG2X so that it's showing more detailed information. If I look into that current job, and then it shows the same information that I show you a moment ago from the network view by searching the particular node that I'm interested in. But this one is, I can get this data from the job ID from the job ID list. Okay. So there is a job level counter statistics. It's showing the send and receive data transfer for that node. So let's go into this historical graph section. So we can search, we can look up the data for the previous jobs. For example, I prepared for another job ID. So put in 110.60779, then it's autocomplete and refresh it. But then it's loading the previous job information here. So CPU usage for the job level, and then I can change to node level, and then it shows. So this is a 2 node jobs. So each node show the CPU utilizations. And more interestingly, I'd like to show this global MPI inter and intra node data exchanges. It takes little time to loading it, but it will be worthwhile to wait for this. So while we are waiting, let me show you another features available. So there is a notification function here. I believe it's loading so that it's slower in this session as well. So notification allow us setting the notification tolerance. If the condition is met, and then it will automatically send the predefined emails about the incident. And the user guide is the INAM user guide that is available from the Embaby's webpage. And this DB size calculator. Okay, it's loading. And let me reload here. Okay, we better to wait on here. So basically, this DB size calculator allow you to calculate the size of database that INAM will accumulate, depending on the condition that you can impose, like how fine grade data do you like to collect, like 30 second, once in a 30 second, or once in a 5 seconds, and things like that. And you can define how long you want to keep the data, so that it will calculate the final database size for you. It's just still loading. So while this is loading, if there is any question, I can answer.
Any questions from anybody?
So live demo has list like this, and but I knew that this takes a minute to load, but it seems it's loading a little bit longer than I tested before. I think we had a screenshot, so there is a question.
Yeah, please.
Reload page.
Yeah.
Okay. So then I can show the MPI primitive information first, because I know that this doesn't take the load time very much.
No, it is that below it is showing some warning. Take a look at your right down screen.
So that it's clear the job ID information.
Okay.
So I need to put it once again.
Okay.
6, 0, 7, 6. Okay. Let me refresh once again, and put the job ID number one more time.
It's also asking for a start and end time, I believe.
So that it's filling up automatically.
Okay. Thank you.
So we don't need this morning. Then MPI primitive information. Okay, it loads faster. So essentially, it shows the MPI primitives usage over time. So during the job running, it shows the data collections pattern here. And more interestingly, it shows the MPI primitives mostly used cases. So MPI I send, MPI all reduce is the first two thing that this particular one used. And if I click on each of the thing, it shows what specific MPI algorithm that was used for this MPI overreduce. And it also shows the message size for different binning sites. So it looks like this MPI overreduce was very small with very small message size, 1 byte to 512 byte on here. So then the thing is, if we can check whether this MPI algorithm is good for this size of message size. And then we can tuning the MPI algorithm depending on the message size that particular MPI communication that will be used. Okay. And for this global MPI and inter and intra node, I have a screenshot took before. Karen, can you post that slide? For now, I will stop the screen sharing.
So there was a question on chat. So the question is this: is an agent running on every compute node?
Also, agent is running on a particular server only, so that each node is just sending the data, so that it does not require the agent running each compute node, so that the overhead is very low.
Thank you.